Hi guys, as promised, we are going to have an FOC session for reheat problem, or we can call it ideal reheat Rankine. In this case, we use ideal. Okay, let's look at the question here. Consider a steam power plant operating on the ideal reheat Rankine cycle. Ideal and reheat. Okay. First, steam enter the high pressure turbine at 15 megapascal. High pressure turbine, steam enters. Okay, steam enters here, and in a state 3 here, 15 megapascal. Or if you can see at the TS diagram, the state 3 is here, so it is in a state of superheated condition, and the pressure here is 50 megapascal. From state 2 to 3, the pressure is constant, so remember that. Alright, and then 600 degrees Celsius, so the temperature is at 600 degrees Celsius. Okay, and it's condensed in the condenser at a pressure of 10 kilopascal. So it is condensed in the condenser at 10 kilopascal. So here in a this one is 5, this one is 6. Okay, so in a state of 6, the pressure is 10 kilopascal. So here the pressure is 10 kilopascal. So after the condenser, the pressure is still 10 kilopascal. So if you look at here at the TS diagram here, the pressure here and here is constant, so 10 kilopascal. Okay, and then the question is, if the moisture content of the steam at the exit of the low pressure turbine, the pressure content here at low pressure turbine is here, so which mean at state 6 here, low pressure turbine is not to exceed 10.4%. The steam is not to exceed 10.4%, or 10.4% is equal to 0.14104. Okay, which means that the steam, isn't it, so the water in the vapor is not to exceed 0.104. the rest is a gas, which means the amount of gas is 1 minus 0.4 is equal to 0.9, what is it, sorry, 0.896. okay, okay, and then we need to determine the pressure at which the steam should be reheated, which means the pressure here, the pressure at which steam should be reheated is the pressure at 4. What is the pressure here when the steam is reheated? So which means the pressure at 4. We don't know the pressure at 4. Sorry, the pressure here 4. We know the pressure here, so the pressure is constant. The pressure here is constant, but once it is reheated, we don't know the pressure after the reheating. after the reheating process. Okay. So we need to find the pressure here at 4, and then the question B is the thermal efficiency of the cycle. So the whole cycle, what is the thermal efficiency? So assume the steam is reheated to the inlet temperature of the high pressure turbine. Okay, so at this position, high pressure turbine, or at state 3, the steam is reheated using the boiler, and then it's before it's enter the low pressure turbine. Okay, so the first step is to find the question A. So what is the pressure of the steam here at state 4? Okay, so how we do it? First, it is given that pressure at 6 is P is equal to 10 kilopascal. Okay, and then the quality of steam at state 6, which is X, we just define is 0, this one, 0.896. This is the quality of steam here, which means the steam is 89.6% gases. The water inside the vapor is only 0.104. Okay, so this is the quality of the steam. The high quality, which means the water is less than the gas. Okay, so the X here, or X6 is equal to 0.896. okay, this is in the saturated mixture between gas and vapor. The area below the curve is in the state of vapor, air and water. Okay, and then another information is S6 is equal to F6 is equal to SF plus X6 SFG, and then we can also find H6 is equal to HF plus X6 HFG. So where to find SF, SFG, HF and HFG? So you need to refer to the table A5. Okay, table A5. At the pressure of 10 kPa, table A5, 10 kPa, which is the saturated. We can also consider it as a saturated mixture. Okay, 10 kPa is here, so your SF is over here, 06492, and your SFG is 74996. This is your HF and this is your HFG. So substitute into the equation. We just use it to calculate the value of S6 and H6. So your SF is equal to 0.6492. Your SFG is equal to 7499996. Your HF is equal to 1191.81. HFG is equal to 2392.1. Okay, so substitute all the value here. So S6 is equal to 0.9492 6492 plus X6 is 0.896 multiply with SFG is 74996. Okay, you will get S6 is equal to 73688 kilojoule per kilogram Kelvin. Okay, is the unit for entropy. So do the same thing on S6, so you will get S6 is equal to 2335.1 kilojoule per kilogram. Okay, save this value for the next calculation. Okay, so our objective here is to find the pressure at state 4. Okay, so since we know that pressure at 4 is constant when it is go through the state 5, which means pressure 4 is equal to P5. It seems like this process 2 to 3 is constant pressure, so 4 to 5 is also constant pressure. So here we can say that if we want to find the pressure at 4, so we can also refer to pressure at 5, because P5 is equal to P4. P5 is equal to P4. So how to find the pressure at 5? So using the information here, since we know that here is, if you look at this figure, entropy for state 5 and 6 is constant, right? Which means that S5 is equal to S6. Okay, so and then the temperature of T5, we know that it is 600 degrees Celsius, which is given in the question. Okay, so those information, T5 is equal to 600 degrees Celsius, and then S5 is equal to S6 equal to 73688. Okay, so we can find the pressure at 5 by referring table A6 to find what is the value for P when the S is the value of S is 7 point something, and then at the temperature of 600. Okay, using the superheated table A6. Okay, just look at the temperature at 600, and then you find at the temperature 600 and then S 7 point something, what is the value for P, for blood pressure. So if you look at the pressure at 4 megapascal, so this is the closest value, which is at the temperature 600. The value of S is 7.3 something. Okay, so we can consider that at this condition, temperature 600 and S is 7 point something, the pressure is 4 megapascal. So here P5 is equals to 4 megapascal. Okay, and then H5, refer to the table AC. At 4 megapascal, the H5 is equal to 3674.9 kilojoule per kilogram. Okay, look at this table. At temperature 600, the value of H is 3674.9 at pressure 4 megapascal. Okay, so you already get your answer for question A, which is so this P5 is equal to P4. So the pressure at 4 here is 4 megapascal, or pressure after the reheating process. So you already answered the question A, which asks you to find the pressure of steam after the reheating process. Okay, so next is to find the thermal efficiency of the cycle. Okay, so this is the same calculation process when you want to calculate the thermal efficiency for ideal Rankine cycle without the reheating process. Okay, same thing. We start from the state 1. Okay, state 1. State 1 here. State 1, what is the information? The P1 is equal to 10 kilopascal, and state 1 is at the saturated line, which is at the saturated liquid. This is liquid, this is vapor, and this is gas, remember? So this line is a saturated liquid. Sorry, okay. So saturated liquid. So refer to the table A5, which is saturated liquid table. So find the H1 or HF at 10 kilopascal. So you will get H1 is equal to 919.88 kilojoule. And then find also the specific volume V1 is equal to Vf equals 0.00101. Okay, at state 2 here after the pump, state 2 here after the pump, so the pressure is equals to 15 megapascal. Okay, and then another information is the entropy, the value of S here from 1 to 2 is constant. Okay, constant, it's not change. If there is a change, the line here will be like this or like this, but it is the straight line, so the entropy is constant from 1 to 2. So S2 is equal to S1. Okay, and then from here you can get the work input or work pump input using the equation of specific value B1 P2 minus P1. Okay, so this is equal to this value 0.00101 multiply with P2 is 15 MPa or 15,000 kPa minus 10 kPa. So you will get the work pump in is equal to 14 kilojoule per kilogram. Remember, we want to find the thermal efficiency. So what is the formula to find the efficiency of the cycle? It is efficiency equals to work net divided by Q input. Work net is work output minus work input. Okay, so we already get the work input. Okay, next is to find the H2. From this equation, what work pump in is also equals to work pump in equal to H2 minus H1. So rearrange the equation, so you will get H2 is equal to H1 plus W pump in. So you will get H2 is 206.95. So save this value for the next calculation. So next is you want to find the we go to the state 3. So state 3, so the information is P3 is equal to 15 megapascal. and then you also know the temperature 3 is equal to 600 degrees Celsius. So state 3 is at the superheated condition, so you need to find H3 at the table A6. Table A6 is particularly for superheated condition. So H3 is equal to 3583.1 kilojoule per kilogram, and then S3 is equal to 6.6796 kilojoule kilogram dot Kelvin. And then next is we go to the state 4. Using the information of P, you just calculate just now for the question A, which is you just get P is equal to 4 for MPa, right? Okay. And then another one information is the entropy for state 3 and 4 is constant, which means S3 is equal to S4. So the state 4 is also at the superheated condition at this region. So you might want to use table A6 and then find the H4, which is equal to 3155.0 kilojoule per kilogram, and then you can get also T4 is equal to 375.5 degrees Celsius. If you refer at the table A6 at 4 megapascal, and then using the information of S3 is equal to S4, so what is your S3? S3 here is 6 point something, okay, so 6.6 something, okay. So at 4 megapascal, and then S is 6 point something, S 6 point six something is between this area, so you need to do the interpolation to get what is the temperature here. So after you do the interpolation, you will get the temperature is 375.5 degrees Celsius. Okay, now you already get all the enthalpy value from H1 to H4. Okay, so sorry, from H1 to H6, you have 6 state here. So using all the information given, you now you want to find from the efficiency formula, you want to find you already get the work input, so you want to find the work output. Okay, so work output or work turbine out, using the formula of reheat, you'll get the formula is like this, work turbine 1 plus work turbine 2. So turbine 1 is here, turbine 2 is here. So your turbine 1 is between state 3 to 4, and turbine 2 is between state 5 to 6. So your formula is going to be like this, H3 minus H4 plus H5 minus H6. Okay, what about Q in? So in order to calculate the efficiency, you need this parameter, work out, work in, and Q in. So Q in, the position of Q in a TS diagram is between this region at state 2, 3, 4 and 5. Okay, because there is a reheat process, so the state at 4 and 5 also included. This is the region where the boiler process is taking place. Okay, so the formula Q in is equal to H3 minus H2, which is in the TS diagram in this position 2 and 3, and then plus 4 and 5 plus hash 5 minus hash 4. Okay, so using those equations, so you just substitute all the value of enthalpies and then calculate the efficiency, which is work out minus work in divided by Q in. Or you can also use this equation, 1 minus Q out divided by Q in. Okay, so you will get the same answer. Okay, so please do this and submit in the Google Classroom. Thank you.